Hey everyone, welcome to The Explainer. Today we're unpacking something absolutely fascinating: how AI models are getting dramatically smarter without just getting bigger. We're going to dive right in by asking the exact question that recent Stanford AI research has been obsessing over. Seriously, how on earth does a tiny AI model completely outsmart a giant one? To really understand the stakes here, look at this comparison. We have a massive 175 billion parameter model, like GPT 3.5, and it absolutely bombs the advanced Amy Math benchmark, scraping by with about a 5% accuracy. But then look at DeepSeek Math. It has only 7 billion parameters, literally a fraction of the size, and it's hitting over 50%. That is wild. How is a model that much smaller performing 10 times better? To figure out how that smaller model pulled off such a massive upset, we're going to follow this evolutionary arc across 3 pivotal research papers. We'll look at the self-improving AI loop, bootstrapping logic with STAR, mastering math with reinforcement learning, taming long reasoning chains, and finally, wrap up with the future of AI reasoning. So, Section 1, the self-improving AI loop, and how we close the feedback loop for AI. Now, the core engine behind this massive leap in performance comes down to a crucial distinction: searching for an answer versus actually baking the reasoning directly into the model. With test time scaling, you're essentially throwing a ton of computing power at a problem right when you ask the question. The AI generates a bunch of answers, and you just pick the best one. But train time scaling, it totally flips the script. It takes those correct, filtered outputs and feeds them backward to permanently update the model's own internal weights. As the researchers point out, if you allow the model to learn from their own outputs by filtering cleverly, you can improve the models even further. What this means for us is that computing power invested in this self-improvement loop can actually substitute for raw model size. You really don't need a gargantuan trillion-parameter brain if you've trained a highly efficient smaller one to continuously learn from its own correct answers. Moving right along to Section 2, bootstrapping logic with STAR, or teaching AI to reason without human annotation. Now, let's be real. No human wants to spend their weekend manually writing out tedious reasoning steps for tens of thousands of math problems. So STAR relies on this brilliant 4-step loop to force the model to figure out the logic on its own. Step 1, the model tries to solve a huge data set of problems. Step 2, we keep only the correct attempts to train on. Step 3, and honestly this is the genius part, for the failed attempts, we don't just toss them. We give the model the correct answer as a hint. Then, Step 4, we ask the model to generate the rationale backward, showing its work to reach that given answer. And we fine-tune the model on those successful new rationales. It's exactly like a student flipping to the back of a textbook, finding the answer key, and reverse engineering the mathematical steps to figure out how to get there. It forces the AI to construct the connective tissue of reasoning. And this works incredibly well for a lot of tasks, but researchers found it does eventually hit a wall. It plateaus when faced with highly complex math that requires much deeper, multi-step deduction. And that plateau leads us directly into Section 3, Mastering Math with RL, specifically looking at DeepSeek Math and the leap in reinforcement learning. The researchers realized you can't just teach a text-based model advanced calculus right out of the gate. So before applying any advanced reinforcement learning, DeepSeek Math set the stage with some clever foundational steps. First, they started with a base model that was already trained on computer code, not just text, which naturally structured its thinking. Then, they meticulously curated high-quality math web pages from the vast Common Crawl dataset. Interestingly, they actively avoided relying solely on dense academic archive papers because, well, those papers often skip over the actual math steps. Only once the model was primed with this great data did they apply highly efficient reinforcement learning. The absolute secret weapon they introduced during this phase is called GRPO, or Group Relative Policy Optimization. This fundamentally changes how the AI evaluates its own success. GRPO is a highly memory-efficient reinforcement learning algorithm that samples a group of answers and normalizes the rewards relative to one another. The real game changer here is that it entirely eliminates the need for a separate, resource-heavy critic model. To put that into perspective, standard PPO algorithms require 4 massive model copies to run, which just absolutely devours memory when you try to scale up. GRPO only needs 3 copies because it ditches that heavy critic model. It works by sampling multiple solutions to a single problem and then calculates an advantage by subtracting the average reward and dividing by the spread. Basically, it grades the AI on a curve against its own alternate attempts. This gives the model a super clear relative hill climbing signal, showing it exactly how to improve without burning through memory. But, as you might guess, things get messy. Section 4, taming long reasoning chains and stabilizing the chaos with DAPO. When you try to scale this group relative learning to larger models like Qwen 32B, the training can totally go off the rails. You run into this exact set of chaotic problems. First, entropy collapses, which means the model gets stuck and flat out stops exploring new solutions. Then response links explode uncontrollably into these massive, rambling walls of text. If the model encounters a truly hard problem, it abruptly truncates its thoughts and spits out toxic training noise. Ultimately, the whole optimization loop becomes incredibly unstable. And yet, despite all of that chaos, researchers still managed to hit an incredible 50% accuracy mark on the brutal AMI benchmark with the Qwen 32B model. But getting there wasn't magic. The DAPO paper had to step in with some highly specific algorithmic fixes to save the day. DAPO stepped in and tamed the chaos using 4 vital mechanisms. First up, asymmetric clipping, which allows the model to make bigger probabilistic leaps without its exploration collapsing. Next, dynamic sampling. This filters out batches where the model gets everything completely right or completely wrong. Because think about it, you can't learn anything if there's no variance, right? So it keeps only the useful gradient signals. Then there's token level loss, which adds specific penalties to stop rambling, garbage answers from getting the same weight as good, concise ones. And finally, gradual penalties, which directly fixes the toxic noise generated by abruptly truncated reasoning chains. All of these work together to keep the AIs strictly on track. All right, let's wrap things out with Section 5, the future of AI reasoning, and what RL actually perfects. So what did this entire evolutionary arc actually achieve? Well, train time scaling is undeniably an incredible tool. It vastly improves majority consistency across answers and makes complex, multi-step formatting much more coherent. Fundamentally, it perfects the model's ability to systematically search its own internal design space for the right answer. But, and this is a huge caveat, it does not teach the model to solve entirely new, out-of-domain problems, and it does not natively inject new, unlearned knowledge into the system. It perfects what the AI already knows, making it remarkably robust, but it doesn't spontaneously create new knowledge out of thin air. Which leaves us with this final, provocative thought to ponder as we look toward the true frontier of verifiable AI. If train time scaling only perfects what a model already knows, what will spark the next massive leap in truly original AI thought? It is a fascinating question. Thank you so much for joining me for this explainer. I hope it helped you visualize exactly how these smaller models are getting so incredibly smart. Keep learning, and I'll catch you next time.